This video will review what we covered in Chapter 6 on inductors and capacitors. So in Chapter 6, we were introduced to the concepts of inductance, capacitance, and mutual inductance. This video will only cover inductors and capacitors and the equations we use for voltage, current, power, and energy. So let's get started here. We want to cover the equations for voltage, current, power, and energy for an inductor, and voltage, current, power, and energy in a capacitor. Inductors and capacitors are ideal circuit elements. The circuit analysis techniques we learned in chapters 3 and 4 apply to inductors and capacitors. And inductors and capacitors are energy storage elements. They are not active elements in that they do not generate voltage or current. They store and release that energy, so they are considered passive elements. Okay. All right. Let's talk about the equations that we use for inductors. Inductors are drawn like this. Inductance is shown as an L and is measured in henries. Current enters the positive terminal of the inductor, and the voltage is drawn like that across the inductor. Okay, the primary equation for inductors, what's going on here, is V of t equals L di dt. And we had mentioned that current through an inductor must be continuous. It cannot be instantaneous. An instantaneous change in current would result in infinite spikes of voltage. So voltage, on the other hand, can be discontinuous and can change instantaneously. To a DC source, current is constant, so di over dt equals 0, which means that voltage would equal 0, and the inductor behaves as a short circuit. The second equation for inductors is for current, which is 1 over inductance times the integral of voltage plus the initial value of that current. Power is expressed as voltage times current, and so we will be using this equation here. So that is L-I-D-I dt. And the energy of stored in an inductor is the integral of the power, and that is expressed as 1/2 Li di, no, Li squared. All right, capacitors. Capacitors look like this, are drawn like this, and the symbol is C, and they are expressed in farads, typically microfarads. And again, the current enters the positive terminal of the capacitor and exits the negative terminal. So the negative terminal is usually drawn with a curve, and the positive terminal is usually drawn with a straight line. The primary equation for capacitors is current. So the current through a capacitor is the capacitance times the change in voltage across the capacitor over time. Let's use orange. The voltage stored in a capacitor must be continuous. Voltage cannot change instantaneously. The current, however, can change instantaneously and can be discontinuous. All right, to a DC source, the change in voltage over time would be 0, which means the current would be 0. And if the current is 0, then the capacitor behaves as an open circuit. All right, the alternate equation for capacitors is for voltage. So voltage across a capacitor is 1 over the capacitance times the integral of the current plus the initial voltage across the capacitor. And again, power is voltage times current, which is, and again, we will be using this equation here. So C times 1/2 CV, and the energy stored or released from the capacitor is the integral of the power, which is, yes, hang on a second, I've got this wrong. So we are using this equation up here. So it's 1/2. It is not 1/2. CV dV dt. Okay, this is 1/2 C V squared of t. So you will notice that there is a duality between inductors and capacitors. And this is outlined in a table, I believe on page 198 in your textbook. And you can keep that table handy, or you can use this when doing your homework problems and taking the quiz. Okay, let's move on. We also talked about simplification techniques for different combinations. Of inductors and capacitors. So inductors in series are like resistors in series. So the equivalent inductance is equal to L1 plus L2 plus L sub n. Inductors in parallel are like resistors, treated like resistors in parallel. So 1 over L EQ is equal to 1 over L1 plus 1 over L2 okay. And capacitors in series are treated like resistors in parallel. So 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus C sub n. I think I will move this guy down. Let's see. here. Okay, and let's go back to this. And let's draw that's kind of a funky drawing, but so you get an idea. All right, now let's look at capacitors in parallel. Are treated like resistors in series. So the equivalent capacitance is equal to C1 plus C2 plus C sub n. And let's draw these guys. So capacitors or inductors in parallel. And capacitors in parallel. And this would be L1, L2, L3, C1, C2, C3. So in this example, L equivalent would be equal to L1 plus L2 plus L3. C, 1 over C equivalent would be 1 over C1 plus 1 over C2 plus 1 over C3. And here, 1 over L equivalent equals 1 over L1 plus 1 over L2 plus 1 over L3. And C equivalent is equal to C1 plus C2 plus C3. If you have two capacitors in series or two inductors in series, you can use the product of the two over the sum of the two to find the equivalent value. So everything still holds. Okay, one more thing that I would like to talk about as part of this review is we'll keep inductors on this side and capacitor on this side. If you have inductors in parallel, uh-oh, what did I just do? Okay, plus or minus V, and let's change its color. So the current going in to this node will be the sum of each of these currents. So here, this is our node, and the current going in, the sum of the current going in is equal to the sum of the current going out from Kirchhoff's current law. So I equals I1 plus I2 plus I3. And we know that the general equation for inductance, current through an inductor, is 1 over L sub n T0 T1 V of T dt plus the initial value. Okay, so if we plug this equation in to each one of these guys, I is equal to 1 over, I'm going to make that a little smaller, 1 over L1 plus 1 over L2 plus 1 over L3 times the integral from T0 to T of V of T dt plus V1 initial plus V2 initial plus V sub 3 initial. No. That should be current. Not voltage. Okay, likewise with a capacitor in series. Let's put 3 capacitors in series. Let's use this color. So this would be V sub 1 and this is capacitor 1, capacitor 2, capacitor 3. So the voltage here is equal to V sub 1 plus V sub 2 plus V sub 3. And the equation that we use for voltage of across a capacitor is 1 over the capacitance times the integral from T0 to T of the current plus the initial voltage across that capacitor. So if we plug this equation into each one of these guys, we would get V equals 1 over C1 plus 1 over C2 plus 1 over C3 times the integral of I of T dt plus V1 initial value plus V2 initial value plus V3 initial value. So we did not really cover this in class, but we will get into this more in Chapter 7. We'll see it more in problems in Chapter 7. So that's the end of this video recording. I will stop recording now and start a new recording for doing the assessment problems.